Awesome. Thank you so much, Alex. Thank you so much for still coming. It's just as usual, numbers are kind of dropping, but that's fine. So thank you so much for coming. Let's enjoy a little bit about representation theory, which was really what got me started with Magma, because Magma is really good for certain parts of representation theory. As usual, it's kind of a computer really likes finite problems, so infinite problems are always very difficult for a computer. It doesn't mean you can't, for example, simulate representation theory of Lie algebras or something, because essentially that's a finite problem. You just need to reformulate it, and you can load extra packages to do that. But I want to use the online calculator, so we're not going to do that. I'd rather show you what you can do with finite-dimensional algebras, most prominently group algebras. Essentially, Magma was developed, the predecessor of Magma was developed to study various properties of finite groups, and that's everything related to finite groups. Magma is just fantastically fast. It's just unbelievable. So let's try to do that. And the way this works is on the website you will find the lecture notes, and if you open them, you will find something like this. And there's a lecture 7 or lecture 4, section 7, and we can just nicely copy and paste again all the various data into the online calculator. So everything should run into the online calculator, unless I have some typo somewhere, which is we'll see how it goes. So the first thing you would do is, if you do representation theory, I hope that is also how you learned representation theory, is you would learn character theory. And Magma is just like absolutely fantastic when it comes to character theory. It's kind of really easy. So we can get us started here. Copy the code, put it in the online calculator. So I hope it's pretty clear what I'm doing. There's a group which we call symmetric group 3, and then I'll ask it for the character table of that group, and the output is just absolutely fantastic. It's a character table, hooray! So what can you see here is the following. So ignore the stuff with p equals 2 and p equals 3. So implicitly, it also tells you something about if you want to do modular character theory. But let's ignore that. So let's ignore this middle slide, middle row, whatever you call it. Then you see the classes. So it just computes the conjugation classes on the go. And just 3 of them, 1, 2, 3. All of them in some form. It tells you the sizes of the classes. The first one is of size 1, the next one is of size 3, the final one is of size 2, and it tells you the order, which is not the size. The order is the order of elements in that class. So the conjugated class of size 3 consists of the simple transpositions. They have order 2, so the order of that class is 2, and the 3 cycles are in the third conjugated class, so the order of that thing is 3. And then maybe the main beast is the character table, which is the square matrix in the conjugated classes, and it just lists the simple characters, irreducible characters. So chi1, x1, whatever, x2 and x3. So x1, as you can see, every row is a character. It's a trivial character. Character, remember, was just the traces of the representation which is fixed on a conjugated class. You can just evaluate that on a conjugated class with some number. The sign character is the second one, and some more fancy character in the final, which is usually called the standard representation. You can easily do that for. I think the last one I did, I just tested that before it started, was something like symmetric group 17 or something. But I won't pull up the character table for symmetric group 17. Well, let's try at least. Let's try 16, and maybe let's not display the character table. Let's just display the number of elements of that character table, just to be safe. I think it took about 10 seconds, so let's give it 10 seconds. Not so bad. So 16 factorial is kind of remarkable that Magma can do that in like 10 seconds. And there are 231 conjugated classes or simple representations. And yeah, you can access the data. So it's really fantastic. I will now show you how to access the various data. So it's amazing. You can do that for essentially every group. So we have some more fancy examples later on. But we can just compare. So if you would run conjugacy clauses, let's maybe just do it. So let's go back to something reasonable. Maybe this guy here. Just run the conjugacy clauses. It will tell you exactly all three conjugacy clauses, with one representative per class, a simple transposition on 3 cycle, and the boring element identity element. For the first conjugacy clause, and then all that happens in about 0 seconds. Let's see. All that happens in 0 seconds. Yeah, very good. So, like, really quick. Okay, well, symmetric group 3, but maybe if you do 10, it will be a bit more sophisticated. So look, whatever it is for 10, and it was still 0 seconds. So there you go. It's like really nicely and just beautifully fast. You can really do that for many things. So you can just set up here, as we've seen in Don's lectures, there's a database. So I take a small group of order 512, and I take the 11,600 group on that table. I have no idea what that group is, doesn't matter at all. And I asked for character table, and it took it 0.03 seconds to do it. It's a group of order 512, obviously. There are 44 characters, and the degree of the 14th character, so degree is a dimension, degree of the 14th character on that table is 2. Apparently, I have no idea what that group is. Let's not worry about that group. It's just remarkably fast. You can do it like this as well. If you want one of the groups, kind of the sporadic groups, for example, you can set up a group by just asking it a group, and then in this case, it's a Hickman-Sims group. It's one of the sporadic groups. We'll see in a second that's quite large, and you can just run the same story. This is a group of order God knows what, and it computed the character table in 0.16 seconds. And there are 24 characters, and the 14th character is of dimension 800 and whatever. So it's just remarkably fast. They can really set up whatever type of fire group problem you have. I think it's not fast enough for the monster, so let me not do the monster here in the online calculator. But in principle, you can just ask it for whatever type of character. So let's go back to the easier one. Just wanted to show you that Magma is just fast as hell. It's just unbelievable. Okay, there you go. Okay. Character table looks hopefully familiar. And the way to access the character table is following. So character 1, for example, is the trivial character, and it gives it to us as a sequence. So 111 is exactly the row in the character table. And if you want an entry, maybe I can do a slightly fancier one. Okay, so here the character is a 201, and if I want an entry of that table, I could just do the following. Second entry is hopefully 0. It's like really like a sequence, but it's not really a sequence. It's kind of fun. So let's try to check that what it actually is. Type. It's not a sequence. It just functions like a sequence. It's algebra character element. So there's secretly the character ring in the background, and it's an element of that ring. In particular, you can do arithmetic. You can add them, you can multiply them, you can whatever kind of character ring element arithmetic you want. So let's do it. Yeah, exactly. So multiplication of characters is standard form of representation. That's exactly that. I will do that for you. I will do that for you. No, it's fine. Ask questions, but yeah, I will do that for you. So it looks like a sequence, but it's actually not a sequence. And well, I just did that here. So I will do that for you. Direct sum. Direct sum is just addition, and tensor product is just multiplication, and it will just give you the character. I will show you in a second how to decompose the character. It just gives you the character, so it easily multiplies and adds the characters together. And the character is like a polynomial, and that's how it treats it. It's just polynomial in the conjugate clauses. You can really do whatever kind of operation you want. You can even create virtual characters which really don't make sense as a representation. You can subtract them if you want. Magma knows that there's generalized characters. You can then ask, is this actually a character? So is this a character means does it come from a representation, or is it just a virtual character, which in Magma is known as a generalized character. So x3 minus x2 is not a representation, but it still makes sense in the ring because it's just a ring. You just add and subtract elements. 4 times x3 makes perfect sense. You can just ask it. Yeah, so x3 minus x2 apparently this one. 4 times x3 is, well, it was 2, 0, minus 1, so now it's 8, 0, minus 4. And it's not a character, it doesn't come from a representation, that's what it means, but it's a generalized character. So it is a virtual character. So sometimes you have this, sometimes it's kind of useful to play around with virtual characters that do not really come from representations, and you can do it because it's just a ring. Magma essentially sets up the characters as a ring. Hope that makes some sense. It's not a sequence, it's more like a ring element. And you can ask really kind of interesting questions. So let's just do some of them. Maybe I pull up the character table again, just to be sure we know what we're talking about. So the third character is the interesting character, x3. And I can ask it, is it irreducible? Or is the tensor product with itself irreducible? Is it faithful? I can ask whether it's faithful. Is it linear? Linear means one dimension. And Magma knows all of this. One dimension. It's kind of a really strange terminology, but linear characters are one dimensional characters. Oh. Yeah, I don't know. It's just what it is. Yeah, it's yeah, whatever. I don't know. It's just linear is one dimensional. And yeah. Anyway, so let's see. Okay, what do I ask? Is irreducible? Is irreducible? Is faithful? Is faithful? Is linear? Is linear? And then you get whatever. True, false, false, true, true, false. So you can even check whether a representation is faithful just by asking a question about the character. I think it's really kind of fun. And Magma knows all of that. And they have plenty of other things you can try. Faithfulness for a character, yes. You can compute it from the character table as follows. A representation is faithful if and only if the degree appears only in the first column. Right? Well, let's look at this one. So this is not faithful, and of course one appears somewhere else. The next one is also not faithful, one appears somewhere else, and the final one is faithful because two only appears in the leading representation. And that's not so difficult to show if you just think of them as the traces of the traces. Yeah. But right. But it's kind of one of those fun facts you usually never hear in representation theory. But you can read of faithfulness from the character table, and it's essentially trivial. Okay. And of course, that's what Magma does. Yeah. So let me run a nice example. Actually an exercise, but anyway, I can still run it. Yeah, I'm still playing here. Well, let me just open a new tab. Run this one here. For and in 2 to 14. I wasn't so sophisticated. Let's just only go to 14. G symmetric group N. I hope that makes sense. I set up the character table. I just make a formal matrix in the entries of the character table, and I fill it with true or false, depending on with 0 or 1, depending on whether it's faithful is true, and I run through the whole character table. So how many simple representations of the symmetric group are actually faithful? In case you ever wondered, this code will tell us, and the answer is just ridiculous. I wasn't aware, but let's see what the code says. So how many injective representations of the symmetric group we have? Takes a while because it runs up to 14. And well, turns out that everything is faithful except the turbulent assignment. In case you have never seen that before, every representation of the symmetric group is faithful. That's right. Right. Exactly. So here, the only one S4 is a bit nasty. S4 has one more entry. So the box representation for S4 is not faithful. But anyway, in case you wonder, I was like, okay. No, I don't think so. You can do a lot with characters, but anyway, faithful is fine. Yeah. And okay, let's just go back to so the character is really a function. So we can actually ask something like, let's go back to this beast. G2, I can tell you what G2 is in a second. G.2, remember that was the notation for the second element in the group, and you can evaluate that one on the character. Because the character is some percentage function. You can evaluate that one on the character. G2 would here, for example, be the simple transposition 1, 2, and I can just evaluate it on the sign character x2, and I should get -1. And get -1. So Magma remembers that the character is actually a function. We can evaluate the functions. And you do it with this x symbol. So whatever, GD5 at whatever that is. There is no fifth one. Very good. Let's do G1. Very good. Whatever. That knows okay, let's do a little bit more so you can more things you can try with characters. The degree is just the dimension, so it's 2 in this case. The inner product is fun. The inner product tells you whether something is summoned. So x3 is the summon of the inner product, if and only if whatever it appears 1 time in this case. So the number that spits it out is the number it appears. The norm is just the inner product with itself. So the total number of elements that we see. So norm here is just saying that, I will do that in a second for you, that x3, tensor x3 has 3 summons. That's why the norm is 3. Inner product just says x3 is one of those summons, and we could find the other ones as well. So let's just try to find the other ones as well. So x1 appears, x2 appears, x3 appears, and that's really just in the tensor product. So 1. The tensor product of the third representation is itself decomposed into the first, the second, and the third. That's what this just says. You look skeptical. Oh, the indicator. Yes, the indicator is. I will come back to that later when I go to different fields. It's a sure indicator. So it is. So characters over complex numbers, and if you want to work over real numbers, that number is the number you need. In this case, geometric group, everything is defined integrally, so there is no difference between real numbers and complex numbers. So the indicator is 1. Come back to the indicator later. Really powerful. So let's try this one, for example. So what I do is the following trick. Get rid of all of the shit here. Okay. I could get rid of this one as well. Symmetric group is still the symmetric group. Character table is still the character table. I take the tensor product and I write down my decomposition, and I remember whatever I've seen in a matrix or in a vector by just writing down the inner products. The matrix you see in a second is just remembering the inner products. So if you do x3 times itself, it contains everything once. So that's the decomposition of the tensor product. If you want to do, let's say, 3 copies, then, well, let's do a count. So it's 2-dimensional. 3 copies, that's 8-dimensional. Yeah, 3 times a 2-dimensional one, and 1 and 1 times into 8. And maybe you can guess actually what the pattern is if I just tell you the next one. That is not so obvious. Now they are 3, 3, 5, whatever. And you could decompose them anything essentially. It's just this little code, and it just goes through the inner products and just gives you the vector, the decomposition vector. I don't know any smart way of doing this directly, but I just set up this little, really not so difficult bunch of code.
This is like the way.
Right, I'm not working with representations right now. The trick is in second while, or maybe in 10 minutes. It gets like tremendously much slower because now you need to set up the whole representation and really decompose the representation. This one is just a silly calculation on a polynomial if you want. That's why it's so ridiculously fast. But yeah, so if you want to decompose the representation, you use this inner product. And by magic, it will give you the correct results. Ooh, let's do this one. This one's fun. Okay. It's actually an exercise, but why not? Another one. What is happening here? Symmetric groups still the same, character table is still the same. I take the 10s to the power, so what do you want? So 1 to 10, the tens of powers. I remember what I see, and well, this one is fun. So I take the sum over everything. We'll see that in a second, and I take. Well, let's get rid of this one here. I take the nth root, so let's just do it. Okay. So you see 1 summoned, that's the first tensor product. 3 summoned, 5 summoned, 11 summoned, 21 summoned, whatever. Count the number of summons of the tensor power, just grows very quickly. Kind of the fun trick you can do here is if you, it essentially grows exponentially, so that's when you take an nth root to cut down the exponential growth. And I cast it into the real field. So real field exclamation mark just means there's a number and treat it as a real number with 10 digits. So that's what you see here. They would do, well, let's just run it.
Okay. You wrote n plus n, you're really basically the number of irreducible sums.
M, exactly. So M is, let me output M, is just a list of things. And this one just adds them all together. And then I take the nth root of whatever I see. Let me just get rid of the nth root first, just to see whether we are on the same page. Right, 1, 1, 1. I get 3 just as a real number because that's a real field somewhere. 3, 5, 3, 3, 5. That's 11. Whatever. 5, 5, 11 is 21, and so on. Cool. Let's get our little friend back. Fun trick you can do with representations. Yeah. Maybe I can be a bit more sophisticated. Go to 14. Yeah, fine. So this number will converge to the dimension of the representation. You can already kind of see that. So the dimension is 2. And if you take the nth tensor power and throw on it the nth root, it will converge to the dimension of the representation. And you can kind of already see that. If you run it a bit further, if you want like something that takes a bit to compute, so let's not do it, and it will go to 1.99, and it's pretty obvious that it will converge to 2. And yeah, this is how so there's the theorem associated to it, and this is how I found the theorem. Just do it, and just kind of, you can read it off. It has to go to 2. There's no other reasonable limit in this case. You would need to do a few more calculations. Fine. So an online calculator, you can run something like symmetric group 18. And on your machine, you probably can do a bit more, like 22 or something. And then you can see the pattern. Okay, I hope this is kind of fun. I decompose it. I add everything together. Very happy. And you can really do a lot of shit with characters. Kind of amazing what is encoded in characters. Let's hope. Okay, symmetric group 5. I set up a subgroup of a symmetric group, which hopefully looks familiar. It's generated by 1, 2, 2, 3, and 3, 4. So H is just symmetric 4. I generate both character tables, and I induce a representation and a restrict a representation. And in order to do that, I really need to set it up as a subgroup. That's why I do this. subgroup of symmetric group generated by. I hope the notation makes some sense. And I can do kind of induction and restriction of characters. So induction of Y3 to G is now whatever in the number of conjugacy classes of S5, and restriction of X3 to H is in the number of conjugacy classes of S4. You just do it, and then you can run again my little code and decompose them. And you would just by miracle kind of get the Young lattice from induction and restriction. A lot of fun to kind of generate the Young lattice. And all of this takes like 0.0 seconds. So what I just tried is Frobenius reciprocity in case you want to see that live proven by Magma. You see what we're in the same group, same subgroup, and I need another one, which is S3. So G is S5, H is S4, K is S3. And I take the character table of in the middle because I want to do restrict, reduce, restrict. And I do restriction and induction. It's kind of interesting. And if you, Frobenius reciprocity tells you that these are adjoints up to an identity factor. So this guy should be 0. So let's see, so induction, restriction, and they differ by an identity factor. So if you restrict and induce and restrict, the difference is identity factor, and you can just get rid of it. So if I would get rid of this one, you would see the character of Y. Three. That's Frobenius reciprocity, live in the online calculator. So induction and restriction are adjoints up to a correction term given by the identity. You don't touch the representation at all. Bash, it's 0. Hope that makes some sense. So you could play so many games with characters. Just insane. You can also set them up differently. Let me skip this one. And let me just, this is again kind of fun. So let's do this one. Okay, I kind of want to force Magma not to cheat. So I set up the symmetric group in a slightly obscure way so that Magma is not cheating. So I set up the symmetric group as a symmetric group S15 as a subgroup of the symmetric group S16 generated by the simple transposition and the long cycle. So for people who have seen Coxeter theory, you only need 2 generators ever to generate the symmetric group, a transposition and the long cycle. And that's what I do. So Magma doesn't know it's a symmetric group in some sense, and it still can compute the character table in hopefully not too much time. 4.4 seconds, and that group is very large. So just for comparison, I list here factorial 15 just to compare, and the size of the group, and yeah, of course, yeah. That Magma doesn't cheat. You can set up your favorite stupid group as long as it's not too insane. It will compute a character table. There are algorithms to do that, and they're really fast. So, yes. You can compute essentially it's a character Sudoku that you solve.
Right.
And you can. There's an algorithm that does that. And there are many others. I'm not quite sure which one runs in Mac, but there are people in the 60s already developed algorithms. That's an older one, right? That's yeah. So we need LF, I see. Okay. Right. But the algorithms are like really classical, like Dixon's algorithm must be 60s or something.
Like one of the critical things is you get
right. Right. So eventually it will give up. I mean, it's still impressive. Character table for S15 from scratch in 4 seconds. Absolutely. I hope everyone is convinced now that character theory is just really fantastic in Magma, and I have plenty of more examples to play around with. So what is this one doing? Oh yeah, maybe I just. Okay, so this one is fun. So let's also do this one. I need to. Like, let me copy it in 2 steps. That's fine. Okay, so if you ever wonder how large actually my little characters get, this one computes, and I'll explain in a second, the average entry in the character table. And it's ridiculous how big they get. So I set up the symmetric group from 1 to 15, character table. I set up a matrix that I will fill later. I run through I and J, which is now column and row. So I pick out a specific entry of the character table, and I add them all together and divide by the total number. So I calculate the average character. Right? So I don't care about signs. I take the absolute value. So this was really what's doing. It's running through the rows and the columns, add them all together, the absolute value, and then divide by the total number. And it's like ridiculous. So let's have a look. It goes up to 15, so 15 is good. Let me go down to 12. Let's see. Back. So okay. That's not very impressive yet. They get arbitrarily large. So in case you get fooled by small number coincidences where you look at character tables, they're not all very tiny. They get fooled down. The square. The number is just the number of characters. This is just the number of rows. But now I'm taking the matrix itself and each entry, so I divide by the square. Yeah, I'm averaging over the number of entries. Make sense? Well, let's see. I think 14 still might work. It's kind of close. I don't know, actually. The people probably know the answer. Okay, what is the largest one you can compute? I don't know, but yeah, maybe I want more. Let's. You think it goes faster than 2 to the n? I would guess they grow super exponentially eventually, but probably not. The online calculator is probably not powerful enough to see that. Yeah, 400. So the average character value is just like large. Then I don't understand.
Oh, well, okay, or I guess this is just like the largest value of the table will be the largest.
That's not clear to me, no. Let me just run the dimensions. The dimensions also get very large.
Oh,
It potentially it is true.
but like that's the yeah. So this is just really confusing. Yeah. The energy
The largest one is probably the dimension. Yeah, so if I average the dimensions, I get much larger numbers.
Yeah.
So dimensions also get arbitrarily large, and you can kind of see that. So number of partitions grows exponentially, n factorial is just gone. So you need a lot of space to fill in the gap, and so the dimensions they just explode. Cool. Okay. So now I would like to work with representations. So whatever you can push in character theory, please push it in character theory, because the efficiencies will just drop. You will see. Okay, so I've just copied the code. We just can run it. Copy this one. in maybe the first slot. Bash. Yeah, we can have a look in a second. The next one again is maybe the next one. That one will be fun. Do it. Run it in the second. Okay, fine. Okay. So metagroup 7 character table, the permutation character. Okay, I set up the permutation character, specific character, fine, whatever it is. I take the 5th standard power and then decompose. That's essentially what I do. Essentially do the same thing as before. And it has a lot of factors, as you can see. 25, 52 times the first one, 0, 1 plus 0. The sign representation and 1, whatever. And it took 0.00 seconds to do that. So that was really efficient. Yeah. So here's the module version. We're not doing the characters. So metagroup permutation module is exactly the same as the module version over the rational numbers. Okay. M, we'll see that in a second. And I just ask for the indecomposable summons and the tensor product. It's exactly the same as in the other code, just with representations. So here I take the tensor power, I decompose it, and whatever I get. And here I just ask directly. By the way, you can ask directly for indecomposable summons, and you can say directly take the tensor power. And we'll see what happens. It's kind of fun. The 5th tensor power doesn't seem to be so sophisticated, and it will give up immediately. Just it doesn't even do the calculation; it just gives up immediately. So the module is 7-dimensional, sure, and 7 to the 5 is too big, so it just stops the algorithm immediately. So there's an algorithm that would run the indecomposable summons, and it does some eigenvalue problem on matrices, and this matrix has 7 to the 5 times 7 to the 5 matrix, because that's the dimension of the representation, and it knows that and gives immediately out. So we don't do that. So this is not a problem with the online calculator. It immediately says, I'm not doing it. Right. So the decomposition algorithm for the representation is just, it's okay, but it doesn't get you very far.
I did for S6 and before the power, and also
It was already enough. I was not trying to find the smallest one.
we can do it for 3.
Fantastic. So it can decompose a 3rd tensor power. And it's really the same problem. I'm just setting it up as a representation instead of as a character. And it's just, yeah. Was just the warning. So please, whatever you can do in characters, do it in characters. Yeah. Don't do it in representation. Right. It's a whole module. It set up the whole module. And that's the whole problem. So with all the matrices and all that fun stuff.
When I ask for it, it gives like list. Oh, some equal to
We will run that command in a second for smaller examples. Yes. But again, this is just the output, as Tom just said. So it actually has the whole module, and I can ask finer information about the module. It just tells me that there is a module of dimension 7. Right, totally. It doesn't work. Okay, but you can still do the following. Okay, so the permutation module is just acting on itself. And I just set up a different group now, not. The GL3 over the field with 4 elements, and I get rid of the center, and the group that you get is called PGL3. And you can do that with any finite. That's essentially my point. And you can just set up a permutation module and you ask, for example, over a field with finite elements, GF is Galois field, GF3 is the field with 3 elements, and I set it up over the field with 3 elements, and it has the whole module encoded, and you can ask, for example, is it semi-simple? And it runs an algorithm to check whether it's semi-simple. And what I just showed you before was the tensor power. All of these algorithms will stop eventually if the module is too large, because it really runs computations with the matrices, and if the matrices are too large, it doesn't know what to do. But this is just dimension 21. And yeah, dimension 21 is fine. But is semi-simple? It's not. Okay, so this is an example of a non-semi-simple representation. You can do that for anything. Set up a group, set up a representation. I show you later how to do that completely general. And then just ask is semi-simple, kind of the same type of questions as for the characters. It just takes longer. Right? So you can do it, but it just takes longer. And in particular, if I have time, but let me just say it right now. What you really should want to do is you want to work over finite fields. Otherwise, it just, yeah. Magma doesn't like infinite fields. Yeah. No computer likes actually really infinite fields. But anyway, well, finite fields is kind of good. Just to show you what this funny group is. Fine. Just pull it up once. Doesn't really matter. It's a placeholder for any type of group. Permutation group of acting on a set of cardinality 21. So Magma, it's a large order actually, so quite large. So Magma sets up groups usually as subgroups of permutation groups, and it tells me it's a subgroup of permutation group of cardinality 21 generated by whatever those permutations. And the permutation representation is the action of S21 on a 21-dimensional vector space. Okay, but anyway. And you can ask something like this. I'll explain in a second what we will see. Okay, so it's not semi-simple. Fine, we already know that. But if it's not semi-simple, what is actually its composition series? So what are the simples in that module? Note that we are really now doing non-semi-simple representation theory, something you can't do with characters. So that's why we need to do it this way, right? Non-semi-simple. What are the composition factors? Is it irreducible? We already had that. Or what are the indecomposable summations? Well, let's see. So it will tell you, and you can access, for example, this is a list, so you can just write square brackets 1 to get the first one, for example. The composition series is so 21, and there's a 1-dimensional quotient that you can take, there's a 20-dimensional module, and then there's a 19-dimensional quotient that you can take, there's a 1-dimensional module, and that's a sequence. It just computes that in seconds, and the composition factors are the quotients that I take. So this is a sequence going from 21 to 20 to 1, and the composition factors are the ones that mod out by the 1, 19, 1. Hope that makes sense. False, what was false again? False is irreducible. No, it's not. And it tells you, okay, there's a 1-dimensional submodule and there's a 20-dimensional quotient. But itself, it is indecomposable. So it is just one sum. So this is an example of an indecomposable, non-semi-simple representation where you have 3 simple factors, a 1-dimensional one, a 19-dimensional one, and a 1-dimensional. And Magma can do that for you. It won't do it for really large stuff. In this example, 21 dimensions, it just takes, again, probably just 0 seconds to do all of that. Something you can't do with characters. That's why we need to do it this way. I hope that's clear. And you can do something like this. If you look at the list, let's have a look at the list here. So I need to access a little bit of finite data. So clearly the 19-dimensional one is not isomorphic to the 1-dimensional one. But what about the 2 1-dimensional ones? They could be the same. They could be different. But Magma can check that because it has the whole representation built in. And what you can do is, let me get rid of the fit here. Okay, set up the composition factors, and I ask whether the first one and the third one are isomorphic. Or I could just ask directly, count with multiplicities, and we'll see what happens. So actually, the first and the last one, they are isomorphic. True. And if I count with multiplicities, you will see here, this one appears twice, and this one appears once, and this is our decomposition factor of the series. Yeah. So Magma knows that this is actually the same. Right? It just outputs the dimension, just for to not to give too much information in one step. Okay, I hope that makes sense. And you can do the following. So there are a lot of constructions that you can play. And the whole point is you need to set up the representation. I will come back to that in a second. Okay, so M is still the same thing. I can take its tensor power, I can decompose it, come back to your question. I can take exterior power, symmetric power, the usual constructions. You could just do it, and here you go. Tensor product is actually really large. So there you go. And the exterior power has the 48. So the tensor product should compose into the exterior power and the symmetric power, and you can just see that it actually decomposes in the Rothen diagram. So it's still non-semi-simple. You still can't split them, but in the Rothen diagram, you just get this nice decomposition of those two appear here, and the other three appear in the exterior. Hope that's reasonably clear. And everything happens in like an instant. So very good. And you can do much more stuff, whatever. You just run this one, and then I have some fun examples. Okay, permutation modules still the same. You can ask what is the Jacobson radical. It will be a 20-dimensional one. You could just take it and tensor power with the previous one, and you get more kind of type of representations. So here, tensor power is something new. The first, so if you take this Jacobson radical, the largest non-semi-perfect summon, with another representation, you can tensor it with the old one, and it turns out that there's some decomposition, and the first one that shows up is the representation we started with. Okay, this was all to show you kind of different, that there are more options, different type of, I have a representation, I can construct a new representation. Because the whole problem here is now to construct representations to begin with. So you kind of want to set them up as easy as possible. Take the irreducible modules, for example. It just can't compute everything directly. There's again an algorithm that does that. So if you have a finite group, let's go over so let's go over the fewest two element. It will compute for you the irreducible modules over any type of finite field you want. Here, characteristic 2 and characteristic 3. It will just compute them for you in a second. It can compute the character, the analog of the character table in this non-semi-simple world, just instantly. Absolutely fantastic. Can compute the projective modules. Just did the same as well. And it gives you a list of the projectives, and then you could access them and then play around with them or whatever. Just instantly can do that for you. Can compute projective covers, injective hulls, all that fun stuff. I'll get rid of all that shit. And I only need X. You just compute the irreducible modules, you could compute projective cover, and you have actually even get filtration, which is very boring because the projective cover in this case is just 8 times the trivial module. So that's what you get as a filtration. Sorry? It's the 8. Exactly. It's 8 times. Okay. Let's have a look again. I take the first one, and the first one is the trivial representation. The trivial representation is always on this list, and it should always be the first one. The projective cover, this beast, the one-dimensional one, is an 8-dimensional module, and its filtration is just trivial module 8 times. There's a coincidence. Oh, this one is a 2 group. That's a good question. Possible. See the second. No, it is not. You're surprised? Well,
I'm just at the projected model. Like they didn't the model.
but the projected cover of the trivial module should definitely have the trivial module inside somewhere.
No, yeah.
Oh, that's just a coincidence. There can be others. It's just
Yeah, I just in this case, I didn't know
whatever. There you go. If you change characteristic, it will something different will happen.
this is the projected.
Of the trivial again.
Okay, you go right now.
In a different okay.
Scroll down.
Down.
So what is the
Okay. Let me show you what it is. I was actually wrong. You were right. So the number of x, the x is just 4 representations. And now, okay, I'm not quite sure what the output is. I take it back. There's some randomized algorithm. No. What?
It's supposed to be just what is the derivative of it, giving you the total.
Yes. I thought the list of numbers was a decomposition, but apparently it's clearly not. There's some randomized algorithm going on. Yeah. X1 is always a trivial one. Oh, that's a good idea. That's a good point. Maybe it's actually not. Okay. Okay, no, it is. So there's kind of fun. So in this game, Magma has stochastic algorithms. So that it initiates a seed and then does the computation, and you might end up with different results. But I think this is not an example of this. I'm not sure what this is an example of this, but I'm not quite sure what the output is. There's clearly a random seed going on. That's something. Yep, absolutely. Okay, so we'll probably figure that out. Yeah. But anyway, it's kind of fun. So you can, over finite fields, you can have probabilistic algorithms that give exact results. And that's exactly what happened here. There's some probabilistic algorithm which chooses a different seed and each time it gives you a different output, but it's still an exact calculation. So I got this one. There you go. Okay. Let me try a bigger example for you. This one is fun. Cyclic group. Okay. I hope cyclic group is fair enough. The cyclic group has Magma constructs for you the irreducible and the projectives and injectives like ED. Indecomposables are much more difficult. Trying to do that right now. Okay. The cyclic group has the easiest example that I have in characteristic 5 has indecomposables given by the Jordan blocks. There are 5 of them, and I label them by Z1 up to Z5, just for the decomposite for the dimension. The first one is a trivial one. The 5th one is projective cover, projective one, and then you have the 3 other ones in between. And I can, for example, produce them for you. I take the following. Okay, Z3 is the 3rd one on my list from before. I have my cyclic group. My field is characteristic 5. I construct the projective indecomposables. There's just one. So let's just put this into another tab. Let's just construct the projective indecomposables. That's just one. I take it. Yeah, fine. That's all that's happening here. And I take its composition series. Because the indecomposable will appear, if you just think of the drawdown block, and you now get rid of one row at a time, Then you can get the smaller Jordan blocks. So just take its composition series. Okay, so there's one of dimension 1, there's one of dimension 2, there's one, 3, 1, 4. I want the third one, I want the 3-dimensional one, so I take the 3-dimensional one, and then I have it set up in Magma, for example. So that's usually a cool trick to get some representations. Go to something projected that you can construct easily and pick them out of the composition series. And this one is indecomposable but not projective. It is irreducible, hopefully gives false, but hopefully it's indecomposable. It's false, it's not irreducible, but it's indecomposable. So that's my friend, the third one on this list. Have a look what we can do with this. That's kind of fun. Okay. And now I take this is an example. I take the tensor powers. So I've set up these 3, and I take tensor power with itself twice. Okay. And I just check what I get. The tensor power with itself twice gives me a 1-dimensional representation, so the 1-dimensional indecomposable, the 3-dimensional indecomposable, and the 5-dimensional indecomposable. Let's make the count. 3 times 3 is 9. 1 plus 3 plus 5 is 9. So that's the decomposition of the tensor product. In case you ever wonder how Jordan blocks in characteristic 5 decompose, this is how Jordan blocks in characteristic 5 decompose. The tensor them. Okay, I've written it down for you. That's kind of interesting. So let me try something funny with this. If you write that down, and I sadly don't have any pens, but anyway, I have my tensor product. Let me just do it in another. Okay, so just the same. Let's try to understand what I'm doing. I'm setting up a cyclic group 5. This is one of my favorite examples. I take this third representation, I put it in the list, 5. And I want to run from 2 to 10. Okay. And I just pick up the various indecomposable summons in the tensor product. But I kind of don't like the projective one. The projective one will eventually dominate everything. So I kick out the projective one. If the dimension is not equal to 5, then I append it and I just keep track of everything on projective. And eventually I run through this loop, which is probably not very smart, but anyway, and I output x, which is the number of summons you see in the tensor product, and I just ask for the number. Okay. So anyone has a guess what will happen? I'll let you make the guess. Let's just ask Magma. So I take the tensor power of my third 3-dimensional representation, and I throw away everything projective and I count whatever. So let's see what we get. 1, 2, 3, 5, 8, 13, 21, 34, 55. The numbers hopefully look familiar. So this is the Fibonacci sequence. So in this case, you can just generate the Fibonacci sequence. So the 3-dimensional representation of the cyclic group and characteristic 5 gives me the Fibonacci sequence like that. And you can kind of see that from the tensor power. Why is that happening? Well, all I said to you is that the third tensor power decomposes into trivial itself and the projective, and I kick out the projective, so I get the recursion x squared equals 1 plus x, which is the Fibonacci recursion. Fine. Hopefully that results. It's one of my favorite examples. You get the Fibonacci sequence. Cool. Okay. So let me at least explain this one. If you are very unlucky and you have no idea how to construct your representation, there's still a way out. Well, not really. If you really have no idea how to construct your representation, there is no way out, obviously. But you can also construct them from scratch. So let me just do it. What's wrong? I want to do it. And you can do it as follows. And it's a bit annoying, so you want to avoid doing this. But anyway, you can. Sorry, we are here. Okay, I set up a group, whatever it is, subgroup of the permutation group generated by whatever. Cool. And I call those generators x and y. doesn't matter what the group is. This example is supposed to show you that they can do it for anything, right? Just some, who knows what it is. Fine. My field is the field with 3 elements, and I set up a matrix for X and I set up a matrix for Y, and then define a G module by just defining the G module of G given by those 2 matrices for the actions of the generator. So I define a module for the action of the generator, and I write down explicit 5 by 5 matrices for that action. Yes, I'm saying generator X goes to a 5 by 5 matrix. Here it is, call it small x. Generator Y goes by, well, I also call it X. Maybe I should have called the other one. Anyway, I send it to a matrix, and I send the other one also to a matrix. And I ask Magma, here's my module, and it's generated by those 2 matrices. There you go.
Why do you need reference to that?
Well, X and Y, oh, very good. X and Y will satisfy some relations. So I can't put an arbitrary matrix here. And this one actually worked. I can't put an arbitrary matrix here.
So like, but I guess the question is why? If here's 2 matrices, really representation.
But it's representation of what?
Like, I guess I want to say. It's like, or just take the algebra generator.
But that's what I'm doing. I take the algebra generator. I just set it up.
But you're like, why do you have to do it? Because then it'd be when because I had 2 matrices and I wanted to like understand the algebra generator. Would I have to figure out?
You could do the same with you could set up an algebra generator like.
But I guess my question is, do I have to actually? I have to do the relations are somehow? Because like, what if I just have 2 matrices and I'm like, I want to figure out. Oh, the algebra.
But that's what I'm showing you right now, because I just made it like typo in my matrix. The Magma Mondays is not representation doesn't work. In order to set up something in this way, you need to know that the matrix is set by relation to one line.
What if I have 2 matrices that don't have relations? Oh, generate.
You can. Yes.
Oh, okay.
Right. So then what I want to do in that case is when you set up the matrix algebra generated by the matrices and ask for permutation. That's slightly different. But yeah, you can do that as well.
You may not know what relation.
Right. No, you can ask Magma for the relation again with the same caveat that as soon as your algebra is too big, something it won't do it. But yes. Anyway, let me not make a typo here. Funnily, the first one didn't change anything. I'm not sure why, but anyway. What now? Okay. So actually there's some computation. It computes whether the matrix is satisfies the relation from those permutations. Yeah, but you can set up essentially any representation this way, right? Just anything. It's just painfully annoying, so you don't want to do it. I could set them up as a matrix algebra if you want. So let's just do that. It's also fun. You could be completely general. Okay, field is characteristic 2. Matrix, this is essentially what we just discussed. Matrix algebra, 4 by 4 matrices generated by those 4 matrices. I will tell you in a second what that thing actually is. What is the dimension of that beast? 4, and I think you could probably ask something like, and it will give you, that's exactly what you ask. It will give you the relation of the matrices. Some new generators. Yes. Just 3 over. I don't need to use. I mean, here's a field, but I don't need to use a field. But I could add some general ring. Fine. Get back to my. It's a 4-dimensional algebra, and anyone has a guess what this 4-dimensional algebra is? And not many 4-dimensional algebra. Okay, I let you wonder for a little bit longer. many four-dimensional algebras. Here you go, it's this one. Just set up as matrices. So if you want representations of that thing, you can just do it. For example, and do is, this one is cool. It's super annoying to do it in practice, but you can set up the whole map if you want, the whole action map. I define a module, which is just a vector space. So V is just a four-dimensional vector space, and I act on it by specifying the map and then saying this is a module with that map. So this is more like the representation I specified by the map. And in this case, it's just really trivial because I have four-dimensional vector space and 4x4 matrices. So all I'm doing is I'm acting by multiplication. And then as soon as you have set it up, you can run everything I showed you. Just indecomposable summons, whatever. And it will it's not, this is the right A module, 4, blah, blah, blah. Okay, there are two ways to set up general representations. You have something given by generator relations, specify the matrices. If you don't have anything given by generator relations, specify the action map. You can do that. And of course, specifying the action map, you can now set up everything. It's just super annoying, so don't do it. Unless you have to, sometimes life's unfair. Sometimes you need to do it. And as soon as you have set it up, you just run the usual nonsense. Okay. And it will essentially don't do it from a certain point onwards, but you can do the usual nonsense. You can take direct sums, so let's just do it. And you can ask for the matrices in those direct sums. M is my module. I have set it up. Now I can do the usual operations. I can take a direct sum and I can ask for the action matrix of my A2, or I can specify a submodule given by basis vectors, and I can ask for the action matrix of those things. So you can really just, as soon as it's set up, you're good to go. Up to the usual, if it's too big, Magma will complain. Fine. So let me finish by doing some fun example again. This one is fun. This one was actually the client for group in characteristic 2. If you think about this for a second, if you take the client for group in characteristic 2 and you specify the generators to be 1 minus the group elements, they will act by the matrices, so that x squared and y squared is 0. So the algebra that I just set up was the group ring of the client for group in characteristic 2. 4-dimensional. There's not much you can do. I can also set this up differently. Small group of order 4, the second one that is not cyclic, that's the client for group. Very good. And I take one of these indecomposable summons, very similar to what I did before. So this one is another one of my favorite examples. Okay. I can generate the irreducible modules. I take its projective cover. I take the composition series and I pick out one element from the composition series, which is of dimension 3. Fine. So there's a 3-dimensional representation of T2, and it's really just the same compared to what we did before. So that's OX. And now I do the following fun thing. For I in whatever, do indecomposable summons of the tensor product, and I only went up to 5 because it will complain, it's 3 to the 5, but anyway, 3 to the 5 is doable, and I just display them. Oh, but it takes a while. This should work. I tested this before, I think. Yeah, there you go. So I just collect all the indecomposable summons, and you will see a 3-dimensional one, a 5-dimensional one, a 7-dimensional one, a 9-dimensional one, an 11-dimensional one. And if you take high enough powers, you see everything. So the client for group is my favorite example of the first non-symmetrical thing that you meet with infinitely many indecomposables. We just generated the first 5 of them. But it, of course, goes on. The next one is 13, 15. And they all appear in tensor powers of the third, the 3-dimensional indecomposable representation. And that's essentially the complete list of them. You can do the same. So 2-dimensional one, you get even dimensional ones. And that's essentially the whole list, but not quite. But again, let's do this. It's just a 5-dimensional tensor product. This is just a 5-4 tensor product.
Oh, wait, okay. First.
Oh yes, let me scroll.
The first case, the first tensor power, you got 3 dimensions. The second case, the second tensor power, you got 5. For you.
Yes, exactly. Okay, let's do the calculation. 3-dimensional one. And there's a projective of dimension 4 because it's Klein forward. That's just a regular. Okay. 3 times 3 is 9. There's a 5-dimensional one in the 4-dimensional. 3 times 3 times 3 is 21. I hope that's right. So there's a 5-dimensional one, and I guess a few copies of the projective one will always. And yeah, in the next tensor product, you'll see the next one and a lot of copies of the projective. Oh, where is my projective? Sorry, what are you confused about?
Oh, just the output. What? Why isn't it? It seems like it's only saying. Sorry, but it feels like it's only mentioning the non-projective.
Yes, and this is because I have a I have a funny line break here. Let me get rid of the line break. I take the I take the indecomposables at the last position. Sorry for the line break.
Oh, so you're only so it's now like
right. So this is just yeah. If I get rid of this, you will see what happens. Ah, maybe I should have made it smaller, but anyway.
Okay.
Okay. Right. So you see the 4-dimensional one like plenty of time, and I just picked the last one to make it nicer. Like this one, I mean 4, 4, 4, 4, 4, 9. Very good. And a lot of 4s and makes sense. So these are tricks that you can't play these characters. But what you can do, for example, you can actually ask for the this one is fun again. So let me just run it and then I'm done. So it's the same setup, same nonsense. I take M to be the indecomposable summons the tensor product, and then I take the last one of them. So I want the interesting one, not the projective representation. Don't get confused by the line break. I'm sorry for the line break. And I can do the following. It's kind of fun. I can make it into a representation. It's a module. I can push it. And I can cast it into the class of representations, and then it's a function. And I can ask the what are the action matrices. So there should be now a 5-dimensional matrix. So G1 is the identity. G2 is one of the non-trivial elements. And on the 5-dimensional representation, the sum x is y. We can really recover all the matrices. So Magma, that's what Don said like a while ago. Magma just gives a small output, but it knows all the matrices inside. So we can output all of them. So really up for it. Sorry? I just added 2 of them. Whatever. But there's a randomized algorithm going on. So actually,
why is it not?
No, the non-projective one is always the last one. I think Magma orders them by dimension. And the non right, but it's 4. And the first one I picked up was dimension 5, and then 7, and then I tricked you. Yeah. Okay, yeah, I think I could stop here. Thank you so much.